Today we're going to take a closer look at the mean of a probability distribution. We know from our descriptive statistics unit that the mean of a sample is equal to the sum of sample values which we can summarize using summation notation, divided by the number of values. Or if we're looking at a population, where we have all of the x values in the entire population, we divide by the size of the population. For a frequency distribution, where we have the same values repeated over and over, we have a similar formula. Let's look at some examples. So here in a situation where we flipped 32 coins, where we flipped a coin 4 times, 32 times, 3 times out of those 32, we got all 4 to be heads. So as we're adding things up to find the mean, we could write 3 plus 3, sorry, I'm writing the wrong number here. We could write 4 plus 4 plus 4, and then move on to the next x value in our distribution, 3, 4 times, 3 plus 3 plus 3 plus 3, and then 2 heads. That x value came up 13 times. That's really tedious. We have an operation that adds all of these up in one step. That's called multiplication. So instead of this formula, with our 3 4s, our 4 3s, our 13 2s, our 10 1s, and our 2 0s, we can use this formula using multiplication instead of addition. We're still getting 12 plus 12 plus 26 plus 10 plus 0. But instead of counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on to get to 32, we're just counting the frequencies. So 3 plus 4 plus 13 plus 10 plus 2, 32 is our divisor. So these products add up to 60. Our n is 32. Our x bar is 1.875. So that is our frequency distribution. But let's go a step further so that we can start talking about probability distributions. Instead of dividing by 32, we can multiply it by its reciprocal. This makes it easier to see how we distribute. This 1/32 can be applied to each one individually. Right? 4 times 3 30-seconds, 3 times 4 30-seconds, and so on. If we want to see this in fraction form, we would say 4 times 3 over 32, and 3 times 4 over 32, and 2 times 13 over 32, and so on. Right? That's what these terms are saying. Well, this 3 out of 32 and 4 out of 32 and 13 out of 32, we've already calculated. That's what the relative frequency is. The relative frequency is the frequency divided by n. So if we turn these into decimals, we get the same values we had up here for relative frequency. In other words, we're adding up the x values times the relative frequency, as opposed to our original formula of x, of the frequency times x. It's usually, we either say f times x, or we say the sum of x times f, I think our textbook uses this format. I often use this format, divided by n. We're just distributing that n to each term, so we're having f over n. That's the relative frequency. Now we don't have a denominator. We've already done all those divisions. For probability distribution, we're using relative frequency as a substitute as our best guess of that probability. And so instead of saying relative frequency of x, we're saying the probability of each x. So let's see what this looks like for an actual probability distribution. Instead of x bar, I'm now going to use mu, because instead of my relative frequencies, I'm going to use our probabilities. We start by writing our distribution, each of the possible x values in this distribution, and then we plug in our probabilities. 0.0625 is probability of 4. That is 1/16. For 3, 0.25. For 2, 0.375. For 1, 0.25. And for 0, 0.0625. Now before we calculate this, it's helpful to remember how a mean works. Remember, a mean is one of the measures of center. It's the balancing point. Each of these values is a certain distance from the middle, and we have different numbers of them. They're weighted differently. They're weighted according to their probability. But if we think of this distribution, especially if we showed the histogram, 0 has this probability, 4 has the same probability. On either side of the middle, they're weighted the same. Same thing here, 0.25 weighted the same as 0.25. 1 away from 2, 1 away from 2 in the other direction. Because of the symmetry of our probability distribution, we should expect 2 to be our exact middle, which in fact it is. As we multiply and then add those products, we do get our expected 2 as a value. A few things to note. First, 0 times anything is 0. 0 plus anything has no effect. I encourage you to always include every possible x value as you're writing things down, even if you're not bothering to type in 0 times whatever, just for consistency's sake. 0 will not always be part of your x values for your distribution. And not every distribution is symmetrical. So we can't just use the mean or use the median to expect that to be the mean, or use the mode, the value with the highest probability, to expect that to be the mean. So whether we know the classical probability that must be the underlying population distribution, or we only have our best approximation for that probability based on experimental data, we can be confident that this formula does work. The mean value is the sum of x times its probability.